Thank you. I'm so happy to be here. I didn't realize this. It feels like a little bit like my wedding, where everyone I see I love, and these are all the important people in my life. Thank you so much for coming. Thank you to Arts Lab for hosting this event. Stuart and Valerie and Mary, they're really great people. And this place, I'll talk about it more later, but it's really a phenomenal facility and resource that I've been coming to for almost 25 years now. So I'm going to start my story in the Tambopata Nature Reserve in Peru. And it is here where a young American graduate student awoke inside his tent to discover this strange object. Has anyone seen this before? Yeah, this happened about 10 years ago, and I remember it happening as it happened because he woke, didn't know what it was. It was very small, about the size of a pencil eraser. He took a photograph of it and posted it on Reddit and asked, "What is this?" Nobody knew. It was a mystery. And on it went, and there was discussion about what it might be and what its purpose was. A little more disconcerting is that he discovered it on the inside of his tent. Later, more of them were discovered. This one was photographed in Florida. And if you look at it really closely, it's really an intricate structure. There's this kind of tower piece in the middle with this perimeter barricade fence around the outside. And there's a lot of speculation about what it might be, some kind of fungal growth, some insect like a spermazoa or a spider or something even more exotic. Eventually, somebody watched this long enough to discover this coming out of the tower. Spiders. 2 spiders, in fact. And the mystery was solved. This is some kind of a spider egg sac. The reason for it is still not well understood. They think that maybe the mother or the father, they're not sure, or maybe they do it collaboratively, build this to trap the spider's first meal so they actually have a chance in life after they're grown. So why am I talking about this mystery? It's because I love mysteries, and I think we all do. And of course, in the natural world, mysteries are abound. In fact, even this mystery, which we think we've solved, the closer you look at it, more mysteries emerge. In fact, one of the strange things about this is that there's always 2 spiders, like genetically copied, like they're always twins. So as a computer scientist, I've always been a little envious because computers, especially when you start out, they're these really logical systems. Everything about the computer we understand. We've built it. It's a thing of man. We understand everything that's happening in it. When we ask it to write an algorithm to sort some numbers, the numbers come out, they're sorted exactly the same. Yet, even here, even in this fundamentally logical system, there are mysteries that arise. And so tonight what I want to try to do is talk about what these mysteries are and how I'm being guided at this late stage in my career to explore these mysteries. And I'm going to do that by showing you my artwork. I'm not going to talk about Etsy. I'm not going to talk about any of my business endeavors, but I am going to take questions at the end, and you're free to ask me anything. So there's several categories of mysteries in computer science. There's the P versus NP problem. So of these computer problems that are very easy to solve, there's other problems that are very easy to check the solution. And are those equivalent? It seems like an easy problem, but this debate rages. And I don't even understand it, actually. Quantum computers, what's going to happen when quantum computers come online? AI and the nature of consciousness. This whole domain is especially relevant to us now in this time because we're living in the dawn of AI. And what does this mean for us? And what does this mean for society? I don't know. Randomness. Computers don't actually generate random numbers. We have to use these tricks to simulate randomness. But is true randomness possible? I don't know. And finally, complexity from simplicity. And this is the domain that I'm going to exclusively be talking about tonight. So building these systems with simple objects and allowing them to combine, why does such complexity come out of those systems? I've been creating artwork since I think I could program. And these are just some quick examples. And more recently, I've started to take this artwork off of the screen and into the physical world using laser cutters, 3D printers, and other robotic manufacturing techniques. So these are some of the things I'm going to talk about. Unfortunately, I'm going to go through some really basic stuff in the beginning, so we have a fundamental understanding of where we're going, and the really weird, mysterious stuff is going to be at the end. So, but I'm going to give you one right away, okay? So here's a circle. A circle in geometric terms is probably the most perfect thing. It describes exactly all of the points a certain distance away from another point. And a circle is a circle anywhere in the universe. And I love this truth. So let's start building this. If we were to place another circle in this construction, where might we place it? Maybe on the edge. And if that circle is the exact same size, its perimeter also goes through the center of the original circle. What if we do it again? Maybe the intersection of those two circles would be a great place to put another one. And continue around, and we've built an object called the seed of life. This is a very common object in sacred geometry. And if we continue that, adding circles, adding more circles, and then particularly we focus on these blue circles here. They call this the flower of life. And I want to show you something really weird. And yeah, I'm going to show you something weird. So if we take these circles and draw a line connecting each one of these circles to every other, if you notice that top circle has a line connecting it to every other blue circle, and similarly with the others, we get this strange object, and this is actually called Metatron's cube. Many of you have probably seen this. But what is so bizarre about this object, and I have to do just a little review and show you the Platonic solids. So these are something that have been developed. These are all the solids that we can create with regular polygons. And these are all of them. There might be more, but nobody's discovered them. So these are so important to philosophers and mathematicians through the ages. They've actually been assigned elements of the way the universe is constructed. So let's return to this object. So here we are with this construction, and the cube is inside there. Not only the cube, but the icosahedron, the octahedron. All of the Platonic solids, the dodecahedron, are represented inside the sketch. And not just these solids. These are three-dimensional objects with their two-dimensional views found inside this most simple construction. Why does this happen? And then there's this strange one, the Merkaba. It's two tessellated or two intersecting tetrahedrons. And the Merkaba object has been ascribed to light or life itself. Very strange. Does anybody know? I mean, by chance, here tonight? Yeah, it's a mystery that we don't understand. Okay, the first concept I want to talk about is that in my work, I do not create things. I create machines that create things. So in this example, we see this fractured colored disk. And I did not necessarily sit down and create this fractured disk. I wrote a program that generates an infinite number of these fractured disks. And you can see how that works. It takes the original shape, arbitrarily chooses a dividing point, divides it, and then just repeats that process on every shape. And so in this way, instead of creating one object, I've created a machine that creates an infinite number of these objects. Here's another example where I've allowed points to be arranged in radial circles, connecting them. These mandalas, here are examples of those. And it continues. So one thing I like to do across my programs is assign the space bar the function of creating a new one. And my kids have learned this, and so when they come into my office and I'm working, they'll go for that space bar right away. And in fact, they've taught me something which is amazing, like hold the space bar down. Let's just see them all as fast as we can. I love this because as a computer scientist, as a programmer, writing programs that work the same way every time, it's enjoyable to write a program that can surprise me. So when it runs, I don't exactly know what it's going to do. So one topic I need to talk about is iteration. Iteration is the process of doing something over and over and over again. And computers are really good at that. So in this example, I'm just putting a dot, put another dot, advance, go to the next line. Of course, it's parameterized, so I can say I want the dots to be smaller, just keep going. Computers are really good at iterating. Did anybody see the anomaly in that? Almost everybody. So awareness of anomaly is the beginning of knowledge. Here's an example of an algorithmic sketch where I'm doing these colored paint strokes, and I'm putting them in this grid. Here they are close up. Something I've learned from the master Edward Tufte is that when you are showing a system where you have many individual items that have unique properties, one of the best ways to show this is using common multiples. So put a whole bunch of them right next to each other, and in that way, instead of just viewing the one, you're able to kind of understand the system as a whole. And that's what I'm doing here. Okay, so let's look at this example. This is a grid of dots. And in this algorithm, I take a dot and I allow it to connect to any dots that are nearby. And doing that, it's allowed to continue that process until it can't find a dot nearby. And this is a parameterized space. So where I'm clicking with my mouse, the X position determines how straight the dots will connect. So the further over here I am, the straighter it's going to be. The further to the right I am, the more crooked it's going to be. And then the Y position of the mouse determines how far it can make a leap before it gives up. So up at the top, it comes very short. Down at the bottom, you can see it gets really dense. And so in this way, I have this two-dimensional parameterized space that creates a variety of images. And here's some examples. So super straight, super long. Super short, super maybe kind of straight. Crooked, medium length. Looking at these two images, these are just random dots that have been randomly sized and placed. Which one aesthetically is more appealing? You can just see all that. The left one? Yeah. Yeah, the left one looks better, right? Like why? Why does it look better?
Negative space.
Yeah, the negative space, that's a great, that's kind of what it is. So here what I've done is taken those dots and I'm ordering them by size. And this is a trick for anyone that's programming. When you are creating objects and sizing them or positioning them, the objects on the left are following the power law and the objects on the right are linear. Linear is really easy to program, but the power law is way more interesting to us as humans because we see it everywhere in nature. So the size of soap bubbles, the size of galaxies, the size of craters on the moon, the size of trees, the length of rivers, all of these systems follow the power law, almost like down the line. And the power law is just an exponential equation, and it's just a little more code to write, but if you do it, your programs will look better. Okay, so we're still in iteration. Iteration doesn't have to just be the placement of things. It can also be instructions. So in this example, I am moving a particle one step at a time. And here I'm doing the exact same thing, but in a three-dimensional field. This is something called a strange attractor. Here there are 100,000 particles orbiting in three-dimensional space. And this particular attractor is called the Rosler attractor. The way this works is a particle is represented by three variables, x, y, and z. That defines where it is in space. These transformation equations on the bottom tell you where the next particle will be based on its previous position. So what I do is I put a particle, and in a strange attractor, I can put the particle anywhere, and that particle will be moved based on these transformation equations. And these strange attractors are a particular class of algorithm where normally, if you just come up with some transformation equations, your particles are just going to fly off into outer space, or they're all going to converge onto a point, do something really boring. But there are these particular classes that do these things where the particles will always fall into these systems, and they're beautiful. And this is an iterative process. Here I've created an algorithm. This is an oldie but a goodie, almost 20 years old, playing around with the idea of friendship. So here these particles are following two rules, and this is going to be a recurring theme tonight. They will try to get closer to the particles that they're connected to and further away from every other particle in the system. And in that way, this kind of dynamic dance happens. And so I use a machine like that to trace out these images. So these are static images, and I'll show you how this works. I think I have an animation here. Here we go. So this is that same system. I've hidden the nodes, I've hidden the connections, and what I'm doing is only drawing the lines, only drawing the connections. And I use a technique called the sand painter, which I'm going to discuss in detail. Right now. So the sand painter was something that I came up with, and I think it's heavily inspired by living here in New Mexico and like all the sand we have. I remember one day taking a scoop of sand, brown sand, and looking at it really close under a microscope, and you realize, it's not brown. It's like every color is in there, and just from far away, it looks brown. So what I've written is this equation that takes 2 points. So any 2 points that are moving across, it draws a line between them, and instead of drawing that line solid, it puts down a certain number of transparent pixels. And so, and in fact, when I say transparent, I mean like 2% transparency. And I'm putting down sometimes hundreds of pixels for every line. And in the end, it gives me a system that looks like this. The lines don't have to be straight. So here, this line, these two lines are kind of moving. They can vary in distance. And the amount of the line or the length of the line between the two dots is determined by a noise function. Okay, this is one of my favorites. So simple, so beautiful. Take a circle, distribute points onto that circle, equidistant points, then draw lines from each point to every other point in the system. And you get something like this. Oh yeah. This object is called the Mystic Rose. Cool name for a very simple object. So here I have 30 points on the perimeter. Here I have 100 points on the perimeter. And I just want to show you how beautiful this is when you zoom into the complexity here. So all of this is straight lines. These are just straight lines connected on dots, equally arranged around a circle. And there's my daughter Sky playing underneath. I printed this. And this is a repositionable wall graphic, and I brought one of those tonight. It's hanging up on the wall. I'm going to give that away. Okay, we're at the end of iteration, and I knew I would be a little tired, so we're going to take a little break here. I want to talk about the Arts Lab. This place is incredible, and it's almost the end. So the Arts Lab is getting a new building on campus in the next couple of years, and everything that's here will move into that building. I've been coming here for 25 years. I originally came here to work on the dome. There's a dome back here, and it was one of the first domes in the country, really, where artists had access to. And somehow they let me in, and I remember I created a dome film, and we entered it in Dome Fest, which was an annual film festival where dome films were shown. And we won Best of Fest, myself and Joe Dean, who was my partner making this dome film. That was the same year that I was working on Etsy. And it was kind of these two things. And I thought, what am I going to do? Like, I really enjoy working on the dome, but I really like what we're doing here with this handmade marketplace. And I chose Etsy at the time, which I don't regret, by the way. But I think it's time maybe to return to the dome. It's a fantastic medium. Has anybody seen a dome film, either here or anywhere else? There's a really amazing opportunity to see dome work here in Albuquerque at the Lodestar Planetarium with Dr. Jonathan Wolf. He does a Fractals Friday. He's here tonight somewhere. There he is in the back. You can go and watch these infinite fractal zooms in the dome at a great planetarium, which is where my wife and I also got married. Okay, I want to jump to combination now. Combination is exactly what it sounds like. So I'm an object-oriented programmer. When I'm programming, I'm thinking of objects. I'm thinking of the things that I'm programming as actual objects. So a physical thing that moves around and has attributes, size, color. And then it's able to connect with other objects. Combination is the idea of taking those and allowing them to combine in certain ways. This is an example, an algorithm called the 9-block. It's something that quilters use commonly, and I was introduced to it by my wife's mother, who made quilts. The way it works is you have a 3x3 grid. You have your corner squares, your edge squares, and a middle square, and then you have an array of shapes. And then you composite these shapes into the final square. You pick a shape for the edge, pick a shape for the corner, pick a shape for the middle, do your rotations so that you maintain radial symmetry, and you get these cool shapes. So it's a very simple idea, but it's amazing the variety of shapes that you instantly come up with. So if I was a designer and I sat down to try to design all these shapes, this would be an hour of work for me, maybe less for others. But if I can write the program to do it, it's like 4 hours of work, but I get thousands of shapes. And I thought I had an example of how many I'd have, but I don't. This is a video game that I made during the early days of the pandemic. I thought, oh, it's the end, might as well do something fun. And I worked on this with my daughters. It was a fun exercise. This is kind of asteroids inspired, where you're the ship flying through space and you get to basically destroy everything. We wanted to come up with something more interesting for the ship. So we decided to use a combinatoric system. So you can see here in the middle, you've got your basic ship shape. And then randomly, we allow other basic shapes, primitives, to be added, circles, triangles, and squares. And right away, you can see I got a variety of shapes. Some of these look interesting, some of them inappropriate. Here's a wider range of those. And it's so easy to generate. Once you've got the algorithm, it's just hitting the space bar, and here's 1,000 new images. It's a great way. It's a fun way to design. Here I've added the ability to have negative space. So in addition to the white shapes, we're putting black shapes on there too. And you can see there's really some really cool spaceships. And we incorporated this into the game, and the player actually gets to develop their ship as part of the game. And someday we might return to that, right? Because it was really fun working on it. But every time I told somebody I was working on a video game, especially parents, it's like, don't do that. There's another shape using hexagonal arrangements. What's going to happen? Yes. Here's another compositional arrangement. This is, I call it flower composition. We hand drew many flower and gem symbols on the iPad, and then wrote this radial arrangement so that every time you press the space bar, you get this this flower mandala. This was inspired by some of the coloring books that we were doing at home, and I had a printer print one of these. So that is a wall graphic that is repositionable and colorable. So it's made to be colored. I need to figure out a way to give that away. We were going to put some secret thing under your chairs and like the random person that sat down, but we didn't do that. So we have to figure out a way to give this away. Here's Sky coloring this one. Okay, one more combination. This is one of my favorites. I call it the invaders. Take a 5x5 grid. Each cell in the grid can be either lit or unlit. And there's bilateral symmetry. So the column in the middle is unique, and then the right side copies the left side. You randomly light the pixels, and you instantly get icons like these. You don't just get these, you get 32,768 of these. Here they are arranged linearly, so in each one of these, only one pixel is being changed. And you can see the variety of invaders that you get. I love the human mind too, because we can look at so many of these and ascribe meaning to them or significance, even though it's just 25 pixels randomly lit. Here's some more. I recently was able to, well, I fortified my building downtown is what I did. I built a big wall, and it was an opportunity to put some of my artwork into the real world. And so I wrote an algorithm that takes a background image, looks at the brightness of each pixel, and then goes and finds an invader of equivalent brightness and assembles this collection here. Then we took these images and we laser cut them into plate steel and created a giant wall and gate for my levitated building downtown. This is the back alley. I don't know if you can see the dragon. You see kind of its eye there. And it's really close under the dragon. In the right lighting conditions, it really does look pretty menacing. And I've never really enjoyed people in my alley doing weird things back there. So I thought, I'll put the dragon and just let them know this is maybe a place they should keep going. It's actually working. There's the wizard hiding behind the rocks. And you can see this. This building's on Silver and 7th in downtown Albuquerque. And the maid and elf. Okay. We're going to talk about recursion now. This basically sums it up. Recursion is a combinatorial process, so it's combination, except I'm not combining disparate elements. I'm taking the same element and putting it inside itself. And so when you do that, it continues on and on and on, kind of like what's going on right here with all of us. Here's the greatest example. So this is a limb object. Sorry, let me start over here. The limb has a rotation. It has a bottom width and a top width. And that's it. That's all I had to program. I said, here's a limb object. And then I say, OK, allow this limb object to make a copy of itself at the endpoint. So here, I've done that. And there's 3 limb objects. And in recursion, you have to be really careful as a programmer, because this is when you want to save your work. Because if you let a recursive program go and go and go, you run out of memory, your computer crashes, you have to reboot. And it happens frequently. So anytime I'm working with recursion, I know I need to be saving my work frequently. Here, I limit it. And I call it the generation. So generation 0, 1, 2, and then I limit the generations to 3. So when it gets there, it just will stop making copies. But you can see what happens naturally. Oh, I'm going the wrong way. Sorry. Well, that's what happens, obviously. So I think this is a 15 generation limit. And isn't this cool? We get a very natural tree-like object. And the recursive motif can be seen in nature over and over again, in river systems, in trees, in the way animal life behaves. Here's some examples. Every time I run this, of course, I'm randomizing the angles and the widths. Here's another recursive algorithm. Different motifs here. So here, what I've done is I've combined 3 different algorithms. I've got the recursive trees on the outside, the mystic rows in the middle, and a power law distributed star field in the background. And this is art here. This is great. I actually really enjoy this. To me, it's beautiful to run this over and over again. Recursion can also be used to subdivide space. So if you take a space, you can divide it, take the resulting space, divide it. Here I've done this long ago in the deep space days. We had a coffee shop, Deep Space Coffee, downtown, and this is a way of grading coffee, and we created this visualization to try to describe the coffee that you're drinking. Okay, I'm going to briefly talk about fractals. Fractal mathematics is the best way to describe the natural world. And it's a relatively new class of mathematics. My wife once made the amazing observation that the reason, and you can correct me if I'm getting this wrong, the reason why we're so attracted to mathematics is because we're built to observe them. In the natural world, we're surrounded by mathematics. In fact, this is out at the Bisty Badlands. And it's a normal state of understanding the world. So we're built to understand these fractals. So when you look at a tree, that's a very fractal object. When you look at the way a stream is moving, it's very fractal. So here in the built environment of man, we don't build fractally. It's really hard to do, in fact. And so when we see fractals, it's like, that's really resonating with me. That is something I can appreciate. I didn't understand why fractals were so cool, really, but I think that's a great insight. The erosionary patterns on the Bisty Badlands. Have you guys been to this place? It's up near Farmington. It's incredible. It's my favorite place in New Mexico. So here we are. Are we 4,000 feet up, or are we right down on the ground? Fractals are self-similar at every scale. And here's some computer-generated fractals using software that's not my own, but I can spend days in this realm exploring these places. And Benoit Mandelbrot said it best, that fractals are the best way to look at infinity. So I've come to believe that coding is a form of magic. And it's not just code that's magic. I love this quote by Alan Moore. Indeed, to cast a spell is simply to spell, to manipulate words, to change people's consciousness. And it's true. So with code, you could say a word or arrange some letters, and somebody can observe that, and you've instantly manipulated, and maybe that's not the right word, you've influenced their state of mind. So with code, I'm doing that, but with the machine, so the dreaming machine. And I've seen code come to life. If you write code in a way that it can be distributed, you can accomplish amazing things. I want to show this example because this is the beginning of where things are going to get weird. This is a circle inversion algorithm. It's a very simple algorithm. It's listed there on the bottom. Basically, if you take a point relative to a circle and you invert that point about the circle, it basically transforms into the circle. You do it again and it'll hop back and forth. And if you keep inverting, it just flips back and forth between 2 points. It's always in the same place. It's dependent on the radius of the circle and the distance of the point. What if I built a system like this where there are many circles, and each time a point moved, it would randomly choose a circle in the field to invert against? So very simple, very well understood. This is what happens. So in this example, there are 10 million pixels every frame. I start the points, points. I start the points randomly somewhere in the field. They randomly pick a circle to invert against, and they continue that process. And what happens is these structures emerge. And when I'm in this world and I'm moving these circles around, or I'm more precisely arranging these circles, I begin to feel like I'm looking into some kind of alternate reality, like an actual place that exists that can be viewed momentarily in this crude two-dimensional way. It's a purely mathematical world, very theoretical, but we've seen over and over again that the world can be described mathematically. So what is this place? And is there anything of value in here? I don't know. For me, there's value in the beauty, and so that's why I've used it, is just to create these beautiful images. Those noises you hear are me sitting at my computer recording my interaction with this algorithm. This is something called entity. It was exhibited at the Ferrophile as one of my first NFTs, like a way to distribute work online. It's an emergent system that has nodes that are allowed to connect and attract with each other. But what's interesting is that it evolves over time. The longer the node exists, the more aware it becomes of its environment. And the behavior changes as a result of that. So we'll just let this go for a minute and watch it. It's almost as fun letting things be destroyed as it is to create them. Make room for the new. I'm typing frantically because every time I press a key, I can create a new entity. But the decay increases in this program. I'm fighting against it, trying to keep it alive. Thank you. Thank you. Okay, I'm going to talk about mazes and complexification. Let's think of a maze as a group of cells that have neighbors. So I've drawn the cells up. A cell is basically a place you can be, and then there's connections to the neighbors. If I build a system like that, then one way to generate a maze, there's many ways, but there's a great technique called the Aldous-Broder technique after the two men that developed it. Pick a square at random. You move into any unvisited cell, neighbor, and you tunnel your way through until you either get to an end and you get to the border, or you cannot move into an unvisited cell, and you continue that process and you get a maze. So if I take a 2x2 cell grid and I create every possible maze in that grid, these are the 4 mazes that I get. And really, these are all the same maze, just rotated, and it's this. So very easy maze, start, finish, 2x2 grid. If I take a 3x3 grid and create every possible maze in a 3x3 grid, this is how many mazes you get. I think there's 27 mazes here, and I've eliminated rotations, but I left in mirrors. So you can see there's a 2 maze and a 5 maze. Those are basically the same maze, just mirrored. 27 mazes for a 3x3. With a 4x4 grid, how many mazes do you think you get? Here's some examples. It's 5. Yeah. Yeah, how did you know that? There's 10,000. 10,816 or something like that. Okay, so this order of magnitude of complexity, just a 4x4 grid, this isn't even all of them. If we zoom out, these are all the possible mazes. Every one of these mazes is unique, and we're not even seeing all of it. This is actually a square image. The top and the bottom are being cut off. Why does this happen? I'm not a mathematician. I have a feeling some people do know why this happens, but I'm amazed by it. This is 50 by 50. You can imagine just how many mazes there are here. I don't know how to do the math to compute it. This one before, I actually just generated mazes all day long, checked to see if I had already made it, and I did that until no more mazes were being generated over like an hour. You can think of a maze as, this is a heat map. So if the start of the maze is that dot that's on the corner, I've colored every cell in this maze based on its distance from the start. So probably the furthest point from the start is this right here. So I've gone through the whole rainbow and I'm back to red again. And you can kind of see roughly how you would solve this maze just by following the rainbow. Mazes don't have to be in grids. Cells can be arranged polar. You know, polar mazes, you can have arbitrary mazes where every cell is very irregular. There's a solution to that if you're curious. So I've generated an algorithm that creates cube mazes, and I've brought one here today. This is a one-of-a-kind laser-cut wood maze. There's a start on one side and a finish on the other. Not very hard, but very fun to hold and follow tactily. And you can see how this is basically how it looks to me before I generate the vectors to send to the lasers. This is a network or a net map of the maze. You can see how the edges connect together. I've created these various levels of complexity, and I want to give this maze away. It's one of my most cherished mazes, but I'm ready to make more. And so the way I've decided to do that, I'm so excited. I created a maze, pretty difficult maze. Ran out of ink here. Don't worry. This one's my copy. I brought other copies here to hand out. In this maze, the first person to solve this maze gets this cube. So how do I know? How do I know who's going to solve the maze first? Well, here's how I did it. Embedded in the maze are these little characters. This is a perfect maze, not in any sense of quality of the maze, but it's perfect in that there's exactly only one solution through this maze. There are no unreachable spots. There are no loops. So there's only one way through the maze. The way that you're going to prove to me that you solve this maze is as you go along this maze, you are going to write down every character that you come in contact with. And at the end, you will come up with a string that looks something like this, and you will email it to me. Okay? And the first email I get with the correct solution, we'll arrange a place and time, maybe we'll have lunch, and I'll give you this cube. So I'm not handing it out until the end. Okay, now, so things are going to get a little weird. I want to talk about emergence. Emergence is a great word to describe the phenomena where complex behavior comes out of simple systems. One of the first algorithms that I wrote that stumbled across this idea of emergence was this one called substrate. This is an algorithm that it's very simple, the rules. A line is drawn straight until it hits either another line or the edge of the screen, and then a new line is created. New lines are created at the right angles of existing lines. So starting with one line, if I just draw that line and let it go and let those rules follow, this is what happens. And there's a great printed example of substrate behind in the middle that you can take a look at. And you can see, you guys know what's going on there with the coloring. I'm doing that with the sand stroke. And the sand stroke is, of course, starting at the line and then occupying the space there. So it's interesting that just this very simple rule, just go until you hit a line and then start again at a right angle to other lines. This emergent pattern forms something that's reminiscent of city planning. Yeah. And according to Google, this is my most popular algorithm, the substrate algorithm. Here is a classic from computer science. In this example, the little red dots can be imagined as being ants. The white dots are grains of sand. The ants are blind and they have no intelligence. The only thing they do is, while randomly walking around, if they bump into a grain of sand, they, pick it up. If they're holding a grain of sand, they drop it. Those are the two rules. I let the ants go. The sand is initially distributed randomly across the field, but over time, if you speed things up, you can see something starts to happen. The grains of sand begin to clump into groups. And if I eliminate the ants, so we don't even see the ants anymore, we can run this a little faster. We just see these grains of sand moving around. And eventually, what happens is that there's one big pile of sand. So my wife has pointed out that I've never actually shown that. And it's because I've never actually gotten there. I just believe it's going to happen. I've run this for a day and it still doesn't happen. So it is interesting, and I did want to try to actually run this out to get one pile of sand. I have seen other people do it. You do get one pile of sand. But the idea is that this emergent quality of a sand pile comes from these agents operating under these simple rules. And if it's weird, you can think about it in reverse. If you start with a giant pile of sand, how could you ever have anything else? Because an ant would pick it up, move somewhere, and eventually return it to its location. I'm going to show you now diffusion. Diffusion is a really interesting computer science problem because it was first imagined by Alan Turing, the father of computer science. And he even did it on paper before he had a functioning computer. He imagined that something like this might happen. This is a pattern that we see over and over again in nature. And you can see what's actually happening here. We all know what's going on. We have these points, and each point has a connection to two points to the left and the right. It's going to stay as close as it can to those, and it's going to move away from every other point, and the resulting shape is something like this. So why is this weird? Well, the fundamental logic of what these points are doing is very simple, yet these very complex shapes emerge that we see over and over again. Something else that's strange about this is, so here's another example. Here I'm allowing mitosis, so the cells divide instead of increasing in size. And I can set some of them to divide and allow some of them to just continue to grow. Here's an example of that. I think I'm fascinated by this because for a long time I wanted to program this because I thought it was so aesthetically beautiful, but I wasn't able to until I finally saw this particular technique of using these nodes with force and repulsion. And here's some examples of the types of patterns that you can get from this system. So here's something weird. In this example, I'm starting the program over and over again with the exact same starting conditions, yet look what happens. It's growing, I'm not changing any other parameters, and every time it grows, a unique shape is created. Like, why does this happen? Okay, I've got one more example. This is it. This is a fun one. This was based off of a program called Clusters by Jeffrey I'm going to have to look up his name. He's an amazing online artist. He proposed a system of colored dots. The dots have two rules. attraction and repulsion. So let's imagine we set up this thing. The blue dot's going to be attracted to the yellow, and the yellow doesn't do anything. What happens? Ventrella? Ventura? That's what happens. Pretty simple. Now if I do it again, but this time the yellow is slightly repulsed by the blue, this is what happens. Now here I've got a pink dot. The blue and the yellow are repulsed by each other, but the blue and the yellow are both attracted to the pink. So what happens in that? That happens. And in fact, if I restart this a few times, you can see almost every time you get a certain kind of shape. Almost every time. In this system, blue is attracted to yellow, yellow is attracted to pink, and pink is attracted to blue. So what happens in this? You get this dance. I love this algorithm too because you can think about this as a metaphor for life, like people in your life, your relationships. In this example, I've got one purple. It's strongly attracted to the green, and the greens are all slightly attracted to themselves. Okay, here I have two groups of dots. The reds are weakly repulsed by themselves, so they want to be maybe near each other but not too close. The white is the opposite. It's attracted to itself, and the red is attracted to the white. So very simple rules. Yeah, it's fun. This is so fun. I sit for hours in front of this thing. So what I've done is created a system where I can essentially create a big bang of particles. And in this next slide, I think there's going to be 5 different particles, and the attractions between them are going to be randomized. And you start to get things like this. I can arrange them in various ways, so Big Bang where they're all in the center or in these lines. And if I may, I'm just going to run this live. So here's the actual program. I'm going to run this so you can see what it looks like from my view. So every time I hit the space bar, I'm getting a new Big Bang. I've got these sliders over here where I can adjust, like this is gray's attraction to yellow, and then this is the distance that they're attracted to them. I can arrange them in groups. I can change the color. So isn't it interesting that these lifelike, almost biological patterns emerge from this simple system? And I think that's the last one. Thank you very much. So I'd love to take some questions. I think we have a few minutes here. Ben in the back.
At the very beginning, you invoked the word spirituality. And you didn't say it again. So if you want to, you don't have to.
Yeah.
Maybe that's the whole point of the thing. But could you talk a little bit more about the relationship between spirituality, mystery, and the dynamism, if that's the right word, between that and art and coding?
Yeah, that's a great question. Thank you. I think, so I'm 51 years old now, pretty late in life, and I'm thinking a lot about my purpose or our purpose in life and God's plan and what's the meaning of all of this. And so for me, the framework that I have to understand the world is computation, which is a pretty limited framework, but it's what I've got. It's what I've spent my life doing. So I like to ask the questions, like where is the truth? What's the truth in the thing? What is my purpose in life? How do I love? How do I share this with children? And I don't know if I'm answering your question, but I don't think I actually have the answers. But I think it's just the view, it's the way that I view the world, and so it's the framework that I'm using to investigate. Yeah.
Your work maps and displays mathematical algorithms, and do you have any insights of what kind of mapping or algorithms turn into beautiful art visually displayed?
Mm-hmm.
Any insights into
When? Yeah, that's a great question. When does it become aesthetically beautiful? So for me, the transition in my life was when I was introduced to Edward Tufte. So he talks about principles of design and lays out very simple, clear rules, like what is a visually appealing design and what is the best, most clear way to convey information visually. And up until that point, I was a programmer like any other, making the most horrible web pages you can imagine. And then I learned, when you're displaying items in a grid, don't draw the grid, just put the items. And instantly it becomes more beautiful. And I don't know where the beauty comes from. I think my wife's insight about fractals, I think we're wired to see certain things beautifully. And I think I was just given a gift at home, being presented with beauty. I don't know if that answers the question. Yeah. Item A.
Is it possible to combine the ant program with this dots program to make it so the ants sort of spell words when they do the same house?
That's a great idea. Yes, it is possible. Anything's possible with computer programming. That's what I've learned. It's just how much work do I want to put into trying to do it. That's a really interesting idea. Maybe we can do that together sometime. That's my niece.
I guess I just have an observation, the repulsion concept that you're talking about. There's a similar concept in nature called crown shy, in which large trees will grow all around each other without occupying the space of the other tree. When you look up, especially in the Pacific Northwest, you'll see this plethora of designs that are reminiscent of what you showed. They'll move right up to the point.
Yeah, I've seen that. It's beautiful. Yeah, I've seen that.
That's just something that you're finding through computers, but it's naturally occurring. So there's this weird cyclical.
Yeah, I think I can even imagine a way of programming that phenomena. It's like a negotiation of the canopies of the trees. Like they're touching each other, and maybe there's some kind of chemical exchange. You're like, you're a little too close. I'm going to move into this area. Yeah.
Yeah, they usually have a very weak connection on new branches that are growing out. So the one with the stronger branch will knock off the little growth stump.
Okay, there you go. Yeah, little power dynamic. In the back. Why haven't I made this more commercial? Yeah, that's a great question. I really enjoy doing the work. I don't enjoy publishing it, writing about it, or talking about it, with the exception of tonight. This has been great. But I really just love doing the work. And obviously, with the success of Etsy, I no longer have to find commercial avenues for this work. And it's allowed me, isn't it interesting that late in life when I can do almost anything, I'm returning to this very fundamental thing that I love doing. I really would like to make it reach more people. I just need help. I need help to do that. Somebody's good at it. In the very back.
Hi, Jared.
Yeah.
I really enjoyed your presentation. I learned how to do entry-level C++ coding this past year for IoT. And one of my understandings was relating it to music. So my challenge for you is how, instead of using images and little icons, if you could apply your programming to music and see what that would happen.
Yeah, thank you. I have tried that, and I'm not very good at it, and I think I need to get better. In fact, later in life, my eyesight is starting to diminish, and so I'm turning to music, and I'm doing synthesis, and synthesizers are a way of applying these generative concepts, but to music. But it's hard. It's harder than I imagined, and so is C++, so good job. Yeah.
So kind of related to what he was just saying, actually, you talked a lot about the art and the math and, you know, the interesting intersections and the weirdness in between the two. It looked like you're using Java. Was that for the
Yes.
programming there?
Yeah.
Do you have specific tool sets that you think people should explore? For
Yes.
that?
Thank you. So I use processing, which is an open source development environment tailored for artists. That's published by MIT. It's free. It has a community of 50 or maybe 500,000 users, a huge active user base. And also, it's relatively unchanged, just like Java, for the last 20 years. And isn't it amazing that you can sit down and program in a language? Now, when I started programming, I had my reference books. I'd have to look something up, write some lines of code, look it up. Now I've got it all. It just flows out of me, and I love that. Because in computer science, they'll tell you computer science is a dead-end job. If you don't continually learn the new systems that are coming, it's over for you. So processing is a tool I would recommend, especially if you're doing art.
But
Yeah.
you do pretty much all of these in processing, or do you use
100%. 100% these days, yeah. Yeah. Yes, Lisa.
You also mentioned in the very beginning that you were guided
Mm.
to do this. Do you feel like, you know, like almost you're channeling and you're just, you know, when you create programs or when you see the results, or what does that mean to you?
Yeah. So I was super lucky as a child. I was 14 and my dad brought home a computer from work. He worked at Sandia Labs. And it was one of the first personal computers on the block. And the only way you could use it is if you knew how to program it. And so he taught me some rudimentary programming, and I got started that way. I have had moments of divine revelation, like you might call it, like, oh my, I need to write this. And the substrate algorithm is one of them. I was sitting in a coffee shop in Santa Fe and noticed a sticker in the window, and the way it had been baked in the sun, and the way it was cracking. And I just immediately recognized the process of how that had